Hello, everyone. My name is Ian Lumsden. I'm a sixth-year PhD student at the University of Tennessee, Knoxville, in the Global Computing Lab. And today I'm going to be presenting work done by another student in the lab, Zach Malcolmus, on optimizing checkpoint restoration for HPDC by leveraging Merkle trees, asynchronous I/O, and dynamic chunking. So to start, given that this is a poster about checkpointing, I want to start with checkpointing. So checkpointing has become increasingly important to most HPDC applications as our systems have gotten bigger and bigger, and mean time to failure of the systems and its corresponding software has gotten shorter and shorter. Because of this, applications use checkpointing to be able to actually survive critical failures on the system. And to that end, most research in checkpointing today focuses on efficient writing of checkpoint data, because you don't want to interfere with, say, a big molecular simulation by spending 10 minutes checkpointing. However, there are other less explored opportunities within checkpointing. And overall, this project is focusing actually on using checkpointing for reproducibility, essentially running an application twice with the same data to get a series of checkpoint histories and comparing those histories to look for divergence and signs that an application is not reproducible. To enable that, though, we need a way to efficiently efficiently read and restore checkpoint data. And so that's the point of this poster. In this poster, we are aiming to accelerate the restoration and recovery of checkpoint data, both just to make that process faster in general, but then also to improve explainability for HPC and AI applications. And we do this by leveraging asynchronous I/O to optimize the scattered nature of incremental checkpointing data. That last point I mentioned, incremental checkpointing, is actually one of the big challenges of this work. Incremental checkpoints, if you're not familiar, involve taking checkpoint data, and for the first checkpoint, you'll store all the data. And for each successive checkpoint, you will only store data that has changed since the last checkpoint. This allows us to massively reduce the amount of data we have and enable much faster writes, but introduces unique challenges, I'll go over in a bit, for data restoration and reading. Now, to understand those complexities, we need to understand the structure of that data. In prior work, we looked at incremental checkpointing involving chunking and chunk categorization. So in our previous work, we took entire checkpoint records, we chunked it into small pieces of data, each on the order of hundreds of bytes to a few kilobytes, and then we assigned each chunk of data one of three categorizations. The first categorization, shown here, shown in blue, are first occurrences. These are chunks of data that have never occurred before in the history of checkpoint files. The second category are fixed duplicates. These are chunks that have occurred before, they're duplicates, and compared to the prior checkpoint, they occur at the exact same offset in the checkpoint file. So you can see here at step 1, we have y at offset 3, and at step I-1, we have chunk y again at offset 3, so it's a fixed duplicate. The last category are shifted duplicates. These are chunks of data that, again, have been encountered before, either within the same checkpoint or in previous checkpoints in the history of checkpoints files. But their offsets in the checkpoint files are different from what we've observed before. So M is a shifted duplicate because it occurred in step I-1 at offset 0 rather than offset 2. And then I and J are shifted duplicates because they've occurred previously within different offsets within the same checkpoint. With that idea of chunking categorization in mind, the four formats for checkpoints that we have considered in prior work and that we consider in this work as well are as follows. We start with full. This is our baseline, and it is a non-incremental approach. What that means is a full checkpoint is essentially you build your entire checkpoint buffer, and you just dump that buffer as is straight into the file system. Next, we have basic. To do basic, we essentially generate metadata for each chunk, and then we record all the metadata and all the chunks that are not fixed duplicates. For fixed duplicates, if you want to recover that chunk of data, you would go backwards in the history of checkpoint files to locate those duplicates. List builds on the basic mechanism in two ways. Builds on the basic format in two ways. First, it splits the metadata between metadata for first occurrences and metadata for shifted duplicates, shown by blue and orange circles. And then it also stores only the first occurrences. To find any duplicates, whether they be fixed or shifted, you'll leverage metadata and the history of checkpoints to walk backwards. And the last representation is tree. This is, again, optimization on the list of format, where essentially we start with all of our metadata per chunk, but then we start working upwards to build a binary Merkle tree. And we search for interior vertices within that binary Merkle tree, for which all the underlying chunks beneath that vertex all fit under the same category: first occurrence, fixed duplicate, or shifted duplicate. As a result, we can condense some of the metadata nodes, for example, to higher level vertices in the tree. So for example, 7 and 8 here become the vertex 3, which is the parent of 7 and 8 in that Merkle tree that we built. The benefits of these iterative approaches are, again, data saving, but it requires some unique ways to do restoration. So in this work, we consider 5 approaches to checkpoint restoration. First, we start with our baseline, the non-incremental full approach. In this, we essentially look for the last checkpoint file in the sequence of checkpoints, and we just load the entire file in the memory in one operation. Pretty simple. Next, we have our first incremental restoration method that we considered, which we use for the basic and list checkpoints, and which we use the naive form of restoring tree checkpoints. In this first incremental checkpointing method, we read all the metadata and chunks from our checkpoint files. We then, in parallel, parse our metadata to rebuild information about where the chunks are located. With that information in mind, we, in parallel, mem copy the chunks from the loaded data from the file system into an output vector, and the output vector becomes the final output of the restoration. For the tree, we can then do 2 levels of optimization, which form our last 2 checkpoint restoration methods. First, we have tree POSIX. This is very similar to the naive tree method. The biggest difference is we just don't read in all the chunk data a priori. So the tree POSIX, we start by reading in all the metadata. We then process all that metadata in parallel, again, to get information about where all the chunks are located. And then, in parallel, we dispatch a bunch of POSIX reads to read only the chunks of data that we need. So instead of reading all the data and then mem copying out of the red data, we just read the chunks that are required. And those reads dump into the output vector. The last approach we have is what we're calling the tree Liburing optimized approach. And this is an expansion of the tree POSIX approach that involves 2 main optimizations. First, we use the Liburing library to enhance our I/O throughput. The way that this works, the benefits of Liburing here are that first off, it eliminates excess system calls. And then additionally, Liburing is actual truly asynchronous I/O, allowing us to add further levels of parallelism to the tree POSIX algorithm. The other optimization here is coalescing our reads around stripe size. This allows us to do our reads in kind of units of work that are best tuned for the design of the Lustre parallel file system, and really most parallel file systems. So in our optimized approach, we first set up Liburing. We asynchronously dispatch a series of reads to read all the metadata. As those reads complete, we asynchronously and in parallel reprocess the metadata that's produced to build our record of where all the chunks are. Then we go sequential for a second and coalesce read requests referring to contiguous blocks of memory into individual requests of at most 4 times the Lustre stripe size, again, to maximize the efficiency of the parallel file system. And then finally, we enqueue all of those reads back into Liburing and asynchronously read the data into the output vector, which we again return. These four algorithms for restoration are our main contribution in this work, besides the results. And so speaking of results, we want to assess these. And our scenario for how we assess these is shown on the right here. So we consider 12 different data sets with different compositions and chunk sizes. In terms of compositions, we consider 4 possibilities, ranging from a 100% fixed duplicate composition that is what you would expect from a very sparse application like a graph application, all the way to a 100% first occurrence composition, which is more what you would expect from a highly variable conventional simulation. Besides these compositions, we also consider 4 chunk sizes and do the size of these individual chunks for our checkpoint files. We consider chunk sizes of 1 kilobyte, 2 kilobytes, and 4 kilobytes. For all 12 of our data sets, and each of our 12 data sets, I should say, consists of 16 checkpoint files, each of size 1 gigabyte, and we did all of our experiments on Polaris repeated 10 times. There's a lot of data to go over here, but to keep it short, we consider 2 main metrics, runtime and memory usage. On the right here, you can see all of our runtimes for each of the 12 different configurations. The main takeaway here is that across our chunk sizes, 1, 2, and 4 kilobytes, the trends are pretty much the same. So in a second, we're going to focus in on just the 2 kilobyte data. But also, if you look at the y-axis, you'll notice that as we go from 1 kilobyte down to up to 4 kilobytes, our runtimes actually decrease. This is an important conclusion because it shows that as we get to larger and larger problem sizes, we can run our, in particular, optimized algorithm faster and faster and faster, to a limit, presumably, but we haven't checked yet. We focus in on just a single chunk size, in this case, 2 kilobytes. We see that in general, our optimized algorithm, which is the last pink bar here, is the fastest. And if we compare it against our baseline non-incremental full approach, we see that for very homogeneous data sets, 100% full or fixed duplicates and 100% first occurrences, our times are actually comparable to full, whereas they can be up to 6 times slower for more mixed data sets. This is, despite 6 times slower sounding bad, this is actually really good because the non-incremental full restoration is what we would expect to run the fastest, because it is the workload that is probably the best optimized for a parallel file system. However, the story gets even better when we look at the memory usage. Regardless of composition, we see that our best algorithm, again, the optimized algorithm, which is the last bar in pink, uses only about half as much memory as the baseline full restoration. So kind of in conclusion, that's our findings, we see that depending on composition of our checkpoint data, we can run roughly as fast as full, which is what we would expect to be the fastest, with half the memory usage. And we see that for even varying more heterogeneous data sets, which have more shifted and fixed duplicates, our time can actually decrease as we increase our chunk size, presenting the possibility of our optimized approach potentially reaching comparable performance to the full non-incremental checkpoint restoration with substantial savings in memory usage. So with all that said, I want to end with some future work. So in the future, we hope to integrate some adaptive chunking mechanisms into, in particular, our optimized restoration algorithm. And then we hope to apply that enhanced version of the optimized algorithm to real-world applications. In particular, we are considering adaptive mesh refinement. Thank you all for listening, and if you have any questions, please let us know.